that we talk about that less than 500 by 2040, and which will grow at the rate of 5% CAGR. And right now, of course, it is around 370 billion. And the contribution from the space industry to the space economy is about 70% today. And that satellite industry will have the different components like satellite manufacturing, launch services, ground equipment, and satellite services, of which the satellite manufacturing, launch services, and ground equipment are expected to grow by 7% at the rate of 7% CAGR, and satellite services 1% CAGR. It's very interesting. And why is it so? Of course, there are different applications which we have seen that these are the emerging applications, and especially the CubeSats are being used for the technology demonstration, experiments, amateur radio, and we are seeing the smaller satellites for the broadband. We are seeing the lot of constellations are coming up for providing the broadband services. IoT, asset tracking, Earth observation is well known, the application, and the disaster management, etc. So, what are the drivers for the satellite, the small satellite industry specifically, which is now contributing or expected to contribute to the global space economy? And the foremost, the important factor is the reduced manufacturing and launch cost. And launch cost is really mind-boggling figure now, the way it is coming down, especially with the reusable launch vehicle. Now we are seeing the today launch cost is around $1,500 per kg, which used to be $15,000. And again, the one projection, I don't know, it looks crazy to us today, but it is that $100 per kg. This is what is going to be there maybe in a decade or so. So this is the major driving factor for the growth of the small satellite. Of course, we will see some more focus on these aspects. Apart from that, in the manufacturing, of course, the lot of technological advancement, 3D printing, additive manufacturing, cloud computing, and the use of the commercial components, which are making the technical standard to be relaxed, and which is again resulting in the reduced turnaround time. And another important factor is the efficient use of spectrum. Of course, not only the higher band frequency bands are being used by these small satellites, but even the same frequency band is being used by the larger satellites in the geo orbit. And the same frequency spectrum now we are seeing that it is now being used in the low LEO or MEO orbit constellation. But it doesn't come, these driving factor doesn't come without challenges. Challenges well known, all space situational awareness related challenges, including debris mitigation or the space traffic management, and because of their smaller size, smaller propulsion, they have to be replaced maybe another 4 to 5 years time. Because now we are relaxing the testing standards, so there is a impact on the quality aspect. And the most bigger challenge what we are seeing is the regulation, how to regulate them. In fact, it's not only the national, even internationally also we are seeing ITU itself is struggling now to really working out the coordination mechanism or methods for the coexistence between the GEO and then such a large quantity of small MEO and LEO satellites. So the challenges we have to overcome, and I think we will see in the coming next decade or so, probably we will be seeing most of the satellites sector will be from the small satellite and CubeSat. The opportunities in India plenty for the industry as well as for startups, especially the manufacturing of satellites. Already we are seeing a couple of startups have come forward and they are going on the production mode for the manufacturing of satellite. The user segment, again, we are seeing that some of the large constellation for the broadband which have the plans to manufacture the user segment in India. Downstream is always has a lot of potential with various applications and services in ranging from Earth observation, IoT, broadband, and the mobility is a special application where we are seeing the in-flight and maritime mobility applications will come up. So now I'll come to the very quickly to the regulatory aspect in India. Now, recently, I think most of you are aware that government has announced the space sector reforms, and as a result of that, a independent autonomous entity called InSpace is created. And the InSpace, one of the functions is to provide the authorization for the space activities by the non-government entities. And when it comes to the specifically the small satellites and CubeSat, the important areas where the authorization would be needed is the operations of the satellite, operations and deployment of those satellites, the establishment of TTC and spacecraft control center, the establishment of the remote sensing data receive station, and of course the data dissemination beyond a certain threshold resolution. Another important activity which now we are initiating specifically for the non-government entities is the registration of the satellites or the other space object as Indian space object, and which involves the lot of processes, including the making the Indian ITU filing through DOT. It has its own ITU process. So some of the cases like amateur, we may have to take the clearance of IARU, and when we do the registration, registration is being done right now by Department of Space, wherein the various factors, aspects like collision risk, debris mitigation measures, the interference analysis, etc., are being considered, and it is ensured that the space object meets all those requirements before we register it as an Indian space object. Apart from that, the operating licenses and other clearances from the other government department also is needed, and that is continue to be regulated by the again Department of Telecommunication or the MIB, MHA, DGFT. There are different types of clearances depending on the case-by-case basis. That is especially for the user and the ground segment. When it comes to the specifically in space role, the first, which I already mentioned, that the issuing the authorization for the various types of authorization for the small satellites. Apart from that, we also facilitate the non-government entities to make the Indian ITU filing in coordination with WPC. We also facilitate registration of those satellites as Indian space object in coordination with Department of Space. And of course, the InSpace has been mandated to act as a single window to all the non-government entities for all these space activities in the country. We also play a role as enabler and promoter for the Indian industry, space industry. We enable the usage of ISRO's test facilities by non-government entities. Apart from that, InSpace is also considering establishing its own technical centers, which would have the facilities for design, testing, assembly, integration of all small satellites, which could be used exclusively by the non-government entities. We also enable the technology transfer from ISRO to the interested party. We identify the technologies which can be transferred, which could be useful to the non-government entities. Apart from that, we are also working on a strategy to create a manufacturing cluster, incubation center, all providing different technical support to the startups and the MSMEs. Of course, taking into confidence the other government department, academia, and the larger industry, which are going to play a major role as a mentor to these startups. We are also working on a strategy how to attract the investment, joint ventures for the Indian startups, and also wherever possible we are trying to work out the scheme where we can make some funding, some sort of seed money to the nascent industries. So these are some of the things which I thought it is more appropriate for the small satellites, CubeSat, and the satellites up to 100 to 200 kg. And I would invite now all the distinguished panelists who will throw more light on the various aspects of the small satellite. And I would invite Tony to take over from me here, and then please take the session forward. Thank you. Thanks for your patience.
Thank you, PK. Maybe with Mr. Karthik, if you can do your keynote, please. Thank you.
Sure.
So, Mr. Govindasamy Karthik is the co-founder and CTO of Antaris.
Thank you, Dr. Jain. Good morning, everyone. How is everyone doing? Very quiet. Can I say good morning from everybody? Let's get some energy going here, because we are talking about design of satellites, so this has to be lost of energy. And I see a young engineer sitting in front of us. What's your name? Venkat. Thank you for joining us. That actually gives me a lot of hope, because that's what we need to start. We need to start from him, really, to learn how to design satellite. So with that, let me go into this one again. I'm Karthik Govindasamy, CTO and one of the co-founders of Antaris. Antaris does software for space. You'll be wondering, software for space? We'll talk about that a little bit. So again, I want to state this here, the numbers games. You're probably hearing from everyone throughout this session, and wherever the conference you go, we talk about trillions, billions. But if you look at the ranges, Dr. Jain just showed a trillion, but you can see 3 trillion in one of the analysts. This is like last year, by this time, there were 68,000 satellites to be designed and built. This year, I'm hearing 250,000 satellites. And next year, it could be 500,000, could be million, who knows? It's really rapidly growing at the rate that we can't even imagine. Why? Because we're already in the game. You can see the launch vehicles has been there. Number of constellations already operating. Ground segments are already working. And this is like, all these are for what? Why are we here? What are we going to with all these satellites? Is it for national defense, or just for communications, climate analysis, or just for profit? Can anyone guess? Why are we building thousands of satellites? All the four? I say we're building for people. Why? Because these satellites are going to enable the life on Earth. It's going to change the way we do our life today, and it's going to really change in 10 years from now the way we're going to operate. You see, 10 years ago, there was no electric vehicle, there was no self-driving cars. So we are talking about that now. So what's going to happen in the next 10 years? We are about 7 billion of us today, right? So the needs of these human beings on the Earth is really increasing on a daily basis. We need to communicate better. We need to cross-collaborate. Think about a situation where you don't have WhatsApp today with you, or internet with you. What will happen? What will you do? What can you do without a cell phone today? It's hard questions. So what's going to happen in the next 10 years? Can we support that? Can the current ecosystem support that? It is not, unless we make changes. Why? The cost is very high, and it's really unpredictable. Timelines are long. So anyone trying to build a satellite will agree with me. You go into designing a satellite thinking I can do it in a year, but after 1 year, you're probably still figuring out ICDs, customers, vendors, disparate hardware and software, and then 10 different things that I need to do. You're totally confused. and already you spent your money and trying to figure out what am I going to do next, really getting to the end game of building and sending the satellite. And resources. I showed you 1 billion of people. Can you guess how many % of those are actually exposed to skill sets that do really need to build satellites? Anyone? Less than 0.1%. How do we get to at least 1% of that? And not only that, because of all this confusion, everybody reinventing things again. If I want to build a satellite, I want to go do all over myself because I don't have the resources, and I'm going to talk to everybody. I want to do everything. I want to design, I want to build, I want to manufacture, and I want to operate. So it's really capital intensive and a lot of operating expenses. So these are the challenges, I think, apart from space debris management, other things, I'm not even going there. I'm just touching the challenges that we're going to have to reach the ever-growing number of designing satellites. It's about going from 10,000 to 70,000 to 100,000 to 300,000 of those satellites. How are we going to build those? Question to you guys. What would we do without Linux today? Do you think you can have Facebook, Google, WhatsApp, your internet, all this cloud computing, everything that we're talking about? Anyone wants to say yes, we could do, or no, we couldn't? Correct. Look at that. There's a small number, 1 million of those certified students. That's where we start from the grassroots. So Linux really changed the game of IT computing by enabling that, providing that open platform so that people can innovate and collaborate. With our smartphones, what do you think we'll do with the smartphones? What did Android do? It enabled ecosystem, right? It enabled app developers. It completely eliminated the hardware in the loop. It said 10 different companies can make the smartphones. That's what Android did. Now, 10 years from now, what would the human do without having this number of satellites? Any guess? So what are we missing? We are missing an open software platform. There is no open software platform today that basically enables this grassroots level collaboration, development, app development, ecosystem development, enabling these global things. That's what we're doing. Antaris is that when I talked about software for space, Antaris is about enabling that software for space, that open software that will enable collaboration, creating ecosystem, abstracting hardware, providing API interfaces for developers and customers to go develop faster. And we have these three steps to do it. It's all in the cloud. You can virtually build your satellite in the cloud. It's a 3-step process. Design. We'll provide you an interactive guide to go through mission analysis, requirements, everything on the cloud. It'll guide you through your design process, and it'll tell you these are your trade-offs. And it also enables in the back end a curated set of hardware and component. You're no longer dealing with physical ICD conversations and trying to figure out which vendor, what is that power requirement, what is that, what is this. So we can enable all those automatically through the back-end system. That's going to give you, through the design process, completely simplify your systems engineering from years to even days, if you have all those components available for your need. Second thing is simulate. It's not about just designing it. You want to be able to simulate it, as if you are actually operating a satellite in space. How can you do it? You need to have a hardware in the loop that is talking to your software in the cloud. That is the part simulate does. Not only that, it's also going to interface to all the simulation tools on top of that through the API, so you can actually bring them into our software, work with that, and completely go through a day in a life of testing of your satellite as if you're operating in space. You can literally issue command and test the satellite in the cloud with hardware in the loop and all the simulation tools running with it. It's almost like a true twin situation where you have a real satellite in space, you have a true twin satellite in the cloud. You can really correlate what you're doing with the simulation. The last one is the fly. Obviously, once you simulate, you have to fly the same code that runs on the cloud. You can now put it into the target hardware and manufacture it whoever the master system integrator they prefer to, and then you fly and you operate. That's how simple it's going to be. So the other way of looking at this, cloud, you have the software. You can have developers interfacing to it to do APIs. and app developments. You have customers logging in, creating their mission analysis, designing their spacecraft into the cloud. And then you have marketplace of components and partners starting to participate with it. And you can also directly work with them and remotely connect with them, remotely test it. Then last but not the least is you need to have someone to build your satellite, manufacture the satellite. Think about what happened in PCs and mobile phones, right? Dell building millions of servers, how are they doing it? That's the kind of scale we need to bring it to satellite design and manufacturing in order for us to meet the number that we're talking about. And of course, once you have this true twin in the cloud, you operate the same thing in space. And there is a continuous loop there. It's almost like a CI/CD in the cloud that's going to happen, where you're learning from the space, your telemetry data is coming back to the cloud, you're constantly iterating through it, and then you're making sure that you're ahead of the failures that's going to happen in space. That's, of course, the simplification is going to save you cost. You can go faster to space, and you have a reuse because it's the same platform. You can have different payloads. If you want to launch a imaging payload one and then SAR payload later on, the same software, but you change the payload. So significant reuse of the platform, software that's going to enable you much faster to go to space. And this is the tool that I talked about, interactive tool in the cloud, that will enable you to go through that process, very simply designing the satellite in the cloud. So we have the software, but we need to demonstrate. If I come and tell you, hey, take my software, it's very simple, go design it, you're not going to believe it. So we are actually going to launch a reference design, a technology demonstrator satellite with our software, showing exactly what it can do. It has 5 different payloads because we can support multiple payloads. It's a distributed compute infrastructure in space. You can scale up and down on your compute needs for your spacecraft. It supports all the radio models that you want to go. Literally demonstrating, several different component vendors. It's being simulated through the cloud, and we are going to launch a spacecraft in less than 10 months. And of course, eventually we have more components. It's going to significantly reduce the time that you're going to build the satellite. That's it. So Antaris software space. If you want to learn more, you can go to the website and send us an email. Thank you very much.
So thank you, Karthik. Thank you, PK, for your introductions. Now we're going to go to the panel directly. Because we have a very small time, short time, 15, 20 minutes, I'm going to actually try to take 10 more minutes of your tea time. Otherwise, we won't be having a good discussion here. So I hope I get your indulgence for this. Thank you. So let me first introduce the panelists. We already have met with the Dr. PK Jain and Govindasamy Karthik. We have Dr. Raghava Murthy from Advisor Center of Space Research, lovely professional university, and the Secretary for the Society of Small Satellite Systems. Then we have Dr. PVGS Jayaram, CEO and Advisor Technology PVGS Consultant. And then we have, sorry, all the papers here. Rupesh, Kumar, Gundapalli, CEO of XDLINX Labs. And we have basically a range of both government and industry representative, also university representative for the session. And now I am representing the Access Space Alliance. We formed in 2019 to represent the small satellite sector. We are based in the UK, but we actually are global in nature, so we welcome members. We have many members, and we welcome members from all over the world. And why we did that? Because remember, Sputnik is a small satellite, because a 67 kilogram satellite, which was launched in 1957, the first satellite ever, artificial satellite, way before geostationary and way before the big constellations that we know about. Over the years, there has been a very small amount of small satellites which have been launched. And I'm talking about things less than 100 kilograms, basically. But only recently, over the last 10 years, there has been a boom, basically, as Mr. Karthik and PK has mentioned. There's been a boom of started with universities and governments and students projects to actually build CubeSats. Since in the year 2000, when the concept of CubeSat was invented in the United States. Now you've seen from the slides the terminology being used, the 6 U's and 12 U's, for example. All it means is that there are 12 times the single CubeSat, which is 10 centimeter by 10 centimeter, another 10 centimeter, basically a cubic size satellite. So what I will do now is I will try to drive the panel with a few questions, because it's quite important that the industry, the sector, the government understand that what we're trying to do with this sector and industry is that because these satellites can be built quite fast, and the cost of these satellites is small, and they're very simple satellites, they need to actually have resources in space and on the ground that can be launched and utilized quite immediately and quite quickly. And also the applications we need to also understand of these satellites. Another typical broadband communication satellites, as you have with the big LEO constellations, there'll be more of the slow speed data and the like even navigation data and even positioning data that are required by some of the applications that we need on our everyday life, and also supporting other industry. So let me start with the first questions to all the panelists here. More recently, a range of companies are being born, basically, and coming out. We see in India, Dhruva Space. Unfortunately, Sanjay was not available to be here today, but he was invited to come. So Dhruva Space from India, for example, Fleet Space in Australia, Swarm in the United States, which has been bought by actually SpaceX, and Hyber and Kineis in Europe, and also Greg Weiler, who's the founder of O3B and also OneWeb, now has a new venture called eSpace. All of them trying to tag into the IoT market, basically, direct IoT, direct to satellite market, basically. So I want to ask you, to the panelists, is IoT connectivity via satellite the next big thing? And then why or why not? And the second question, I may remind you the question afterwards, what are the challenges of these companies that are trying to come out now? What are the things they need to tackle to make their business successful? So maybe we'll start with you.
Can I speak? Yeah.
Please, yes. On the microphone, speak from the front, because the microphone is very directive. Just on the front of the mic.
Yeah. Hello. Good morning to everybody. I'm basically right from the beginning, I was a satellite systems engineer, worked from all IRS series of satellites, and I had the opportunity of developing rather new buses for the small satellites also. So previously I was in Cartosat-1, which was I was a project director for Cartosat-1, Saral, and bigger satellites also. And it was 1560 kg satellites, and most of them I have worked in system engineering of the remote sensing satellites. And then the task given by chairman was to make the small satellites, and I could, with my teams, develop 2 buses, that is 100 kg class bus and 450 kg class bus. And those, both of them were used for remote sensing in different applications. And further it was carried on. And now actually the 100 kg class bus is given for production. We targeted the design of the satellite in such a way that it is producible. That is, the basic satellite design should be able to accommodate the different kinds of payloads and different kinds of missions. And that is the criteria at the design level that you have to do, so that it is usable for different payloads. And multiple satellites are definitely required when you come to the constellations of the satellites, where thousands of satellites are going to be there, and addressing many application and services for the communities and governments. So this is one thing. And I also guided the universities in making the 1U, that is pico satellites, and nano satellites, that is 2U configuration and 3U configuration, and also a specific 30 centimeters by 30 centimeters, that is cube. satellites also specific design for that particular applications. But everywhere what we have addressed is what should be repeatable, and when you are designing it, you should design it to accommodate higher capability than what you have envisaged in the beginning. So you have to have an idea of what are the things that are going to come. Definitely, a small satellite cannot do very, very big things. If you want a big focal length, you require a bigger satellite. That also can be a small satellite if it is a 500 kg lesser than 1000 kg satellite. So where you are targeting, and most of the what I have found is femto satellites and nano satellites have got a limited capability. You cannot put all kinds of pillars, but definitely this gives a very good experience, hands-on experience for the academicians and students, so that they get to know of the entire thing, as to from the concept to completion and doing the mission. They will have hands-on experience, and that makes them eligible for making a bigger missions. And now this is a great opportunity, as the number of satellites are in thousands that are going to come, and when multiple satellites, and for such kind of missions if you are supplying, it is a favorable thing for any business. So business has to be better, faster and reliable. So if you can meet these three things, that is better is, Tony sir has asked me about remote sensing. Now so far you receive the data, process it on the ground. That is no more valid today. You cannot take days together, or you cannot take even hours together. You will have to produce onboard processing, and for most of the applications which do not require very high inputs, it is some 70 to 80%. You should process the product there and deliver the product directly to the ground. Not that some ground system is working that and then redistributing it. So onboard processing is necessary for the remote sensing payloads. So you should get that, and also, and your flexibility in the position of the satellite in the orbit has to be increased. It cannot be that it cannot move away from that within the lifetime. Okay. So if it is required, you should have an intelligent control system in order to maintain that. And you also should have the number of satellites linking. So satellite to satellite linking and acting like a member in the constellation is a quality which you have to build in every satellite. Otherwise, it will not be useful for the constellation. So when you are building designing a satellite, it should be qualified or rather constructed with a quality that it can be used in the constellation. What is constellation responsibilities? That's a very big subject. Okay, all these things I'll be able to tell, but time is not there. So constellation capable satellites have to be produced, otherwise number that you can produce in cell will not be there. So all these points, better, faster and reliable. All these 3 points should be covered. Thank you very much.
Thank you. Let me bring in actually as well, since we heard from you at the very beginning, to our 2 other panelists before, Mr. Jayaram and Rupesh.
Yeah. Good morning, everybody. So I'm going to focus on certain opportunities that we have in the space industry in India, and also wish to express my views on what are the challenges from the policy point of view, and those issues that we need to bear in mind while entering into the entrepreneurship in Indian space industry. So a lot has been said about the space economy, that we have been seeing a lot of figures that we see going into $1 trillion. But if you see what's happening with the GDP, space economy in terms of GDP, budget overlays of the government of India, it has come down from 0.26% a decade ago to 0.19% of the GDP. So that clearly says government is not spending. Government is actually reducing its expenditure. So if government is reducing expenditure, how does space economy grow? And even if I say in terms of the budget overlays, in the last 3 years, we have actually come down from over 43,397 crores in 2018-19, we have come down now to 36,794. So there is a conscious effort with the government of India to reduce that space budget overlay. But at the same time, if you see the two policies that they have brought up, one is Draft Space Activities Bill 2017 with wide negotiations, which of course yet to be taken forward, and the National Space Policy Bill that has been already submitted to the PCS, which will receive approval any point in time. So I would like to focus on these two bills and tell you, despite India trying to do a lot, Government of India's initiatives and by bringing in space itself is a huge step forward. We have got NSIL, which is helping the industry. We have got ISPA, Indian Space Association, that has come up. And also there are different space agencies, and with DRD also we have got DSP. So there are a lot of initiatives that government is taking. But despite that, in these two policies, so there are some points that I would like to highlight, which may have to be corrected in some point in time. Now the dispute settlement mechanism in Indian space industry is actually very poor. That we all agree, because we are evolving. We have seen one major dispute in terms of Antaris and waivers, and that has not been good. So sometimes, unless we address these issues and provide robust mechanisms to address legal disputes whenever they happen, this can be discouraging for the private investor. Next is brain drain. If you see, we have over 50 startups. We are seeing more and more budding entrepreneurs. But even after that, if you go on internet, you will see equal number or maybe more entrepreneurs are actually outside. They're all doing good businesses outside. That only shows that the opportunities here are not enough, not adequate. But despite knowing that space economy would grow to maybe $3 to $5 trillion by 2040. So we need to encourage these people to come back. So we need to work on that. Second is the big constellations. Like Dr. Murthy was mentioning, that we need to go towards small satellites, CubeSat, larger constellations. But we have seen just 3 days ago, we have launched 36 satellites, which are big. And most of the satellites that we have launched today, if you see the ISRO's history, we launched bigger satellites, smaller constellations. That's not because we do not have capability. That's because the space infrastructure in India is not yet geared up to take care of this. That's where Tony's point that IoT is very, very critical. And how do we make sure larger constellations of small size we have to go in for. So this is where the private space industry has to come in. If we do not have too many earth stations, too many ground stations, private industry will have to pitch in. The network will have to go in for wireless satellite communications, and that's where there is huge opportunity. Next issue that gets left out in the policy is the organized mentoring and training to these budding entrepreneurs. They have ideas, they have education, they have knowledge, but what they miss out is the policies, how to go through. They get stuck with defense procurement procedures, they do a lot of initial spending, they come to a large stage and they don't understand why the project is not through. So probably here armed forces, the government of India will have to come out and educate them and mentor them so that they can do a good job. Next is this, InSpace has come up with a single window policy that's very good for all of us, especially those budding entrepreneurs, and make use of this so that any policy gaps which you may be assuming, which get clarified there. And also this website is evolving. Now the 75 space challenges have come up. That shows an intent of the government of India, how they want to fund, though there's a lot of funding would be required, but that will give you a fair idea about what kind of technologies we should focus more on. Other aspect that is missing on this draft bill is the export quality projects. What is it? In case if you want to have more Indian exports in space sector, so government will have to focus and say, these are the projects that will be for exports in addition to being used in India, and the funding has to come in correspondingly. So we cannot say we'll give you 1.5 crore and do this project, so that may not work out. And coming back to the national space policy. National space policy is actually now almost on the stages which will come up now. We have heard Secretary Ministry of Information and Broadcasting, we have heard Ministry of Health in the morning, Secretary, Department of Telecommunication. So there are other ministries also who are stakeholders in space industry. But their names and their how they will contribute is actually missing. Secondly, United Nations has space cells. Ministry of External Affairs has a huge role in taking our space industry forward. So how do we use them? That aspect also is missing in the space. So some of these aspects are actually challenges which of course industry will not be able to take care. Government of India will have to take care of it. So we will continue to send these recommendations as and when we get an opportunity. Thank you.
Yes, thank you, Rupesh. From your international experience with Planet and other companies, I think it would be useful to hear from you on the views on the question I asked earlier. Thank you.
Good morning, you all. Thank you, SIA, for having me here. Just a little bit background. I am Rupesh Dandupalli. I am with XDLINX Labs. We are after building the hardware, space hardware platforms for both CubeSat and the Smallsats, powered by the Antaris space software platform. I'm also part of Antaris as the SVP strategy and operations. Before this, I was with Planet Labs. We enabled building this, the mass manufacturing of this satellite CubeSats, and we were part of this, the most historical event of this PSLV 37 launch, on which we launched 88 satellites, 3U CubeSats. Just to confine to the question about this IoT connectivity, to me, these IoT connectivity is more of a enablers for most of the situational awareness use cases, especially in this the telehealth, logistics, communication, and border patrolling. And this is more of a low-hanging fruit where things can be developed and take it to space and leveraged at the kind of volume. And the challenges from the industry in developing these IoT devices, the only thing I would think of any company, we need to just focus on what we are after from the use case point of view, and also careful about what we want to sign up to develop in-house versus leveraging from the industry what is technology out there.
Thank you. Before we go to the next question, maybe Dr. Jain and Karthik, do you have any things to add?
Yeah, I would like to just add to your question. The IoT, certainly the answer is yes. That is the big thing, next big thing. Billions of devices have to be connected, and that is the reality. So, especially large country like India, now satellite would be a very useful medium. We don't have the connectivity, terrestrial connectivity, 5G, 6G, and all that thing across the country. Satellite is going to play a big role for IoT. Thin route applications are the order of the day. Challenges, I already mentioned in my moment the number of satellite increases, naturally the challenges comes in terms of managing the interferences, the collision, space situational awareness, spectrum, many more challenges apart from what he mentioned about the manufacturing itself and all. So and the quality. When we certainly compromise the quality when we go for a very large production, and especially at lower cost. So that is what I want to add.
Yeah, spectrum actually is a big challenge because I'm finding companies not actually finding enough spectrum or spectrum available for their applications. And actually the ITU at WRC-19 made a big mistake not to adopt new frequencies as well. So.
Yeah, so I'll make it quick. Relevant to your question, answer is yes. Obviously talked about billions of devices, and I showed you guys 7 billion people to be connected. So that's the reality. 7 billion people on the yacht with the devices and autonomous car, vehicle, smart city. You think about anything that's going to happen in the next decade, IoT devices it's going to happen. So the challenges, I think I already covered, is the supply chain constraints is going to be the longest one, and the bespoke hardware and software. And if we're going to really manufacture those kind of things, if you have, if all of you can know, if you have 10 different devices at home, PCs and mobile phones, how did that happen? Think about that. If you want to do the same thing, bring that kind of thing to satellites, then it's important to have a platform. Again, I'm trying to go back to the same thing. You got to have a platform that will enable the component replaceability from a supply chain point of view. So the companies you mentioned, they have announced about 100,000 satellites. Right? So how is it going to happen? And we are actually talking about thousands of satellites to build 100,000 satellites. Obviously things have to change in terms of how it's done today to have a software platform and then a hardware that's going to complement to that and ecosystem that supports it.
And likely the industry should actually self-regulate itself with regards to space debris. When you actually go and launch these CubeSats, which have no maneuverability and may within 6 months to a year actually die, stop from functioning, there needs to be ways to actually bring them down to the orbit. Let me ask, we have only time for one more question. I'm going to take over 10 minutes from the tea time to ask you this question for everyone again. And we'll start with you, Rupesh. There is an aspect of satellite communication which is often actually forgotten. It's the ground segment, basically. It's quite important because the ground segment is where you get your data from your application. So often it's overlooked, and there are two important aspects here. There's the satellite terminal, the satellite devices, IoT devices as such, which connect to the satellites, but also the gateways and the core network. The gateways meaning the sort of, when you bring it down to the access point on the ground, and the core network, which is usually forgotten about in the design, and it's always left at the end in a way. What are your takes on these key features, which are also key enablers, in fact, for the small satellite constellations, the CubeSats constellation as well as the other mega constellations as well? And what recommendation would you actually give to stakeholders when they need to consider the ground segment at large, in a way?
Yeah, so while you're saying this...
You have to talk from the front, otherwise...
Yeah, can you hear me? Yeah. So while we're seeing the growth in this satellite volume manufacturing and the demand for this, various satellite missions getting into space, yes, I think the ground segment being totally overlooked, and there is no enough capacity to actually so every mission we've been lately brainstorming, the biggest challenge where we have is the with the ground segment, how we can actually manage these constellations in terms of ground stations and relays and data relays, that kind of use cases. I think one trend we've seen with the this cloud part, the cloud suppliers like Amazon, Microsoft, they're actually getting into providing this as use-based ground segment services, their deliveries. Besides planning for setting up low-cost LEO ground stations, on-demand basis, basically.
Thank you. Good job.
Yeah, we need to move away from the fixed central archival facilities, the storage systems, to decentralized systems in case we want to actually leverage what we already have. So the establishing a ground station with each constellation launch, it cannot happen. And we need to also collaborate with the international community. We should have more Earth stations in the African continent, or maybe to east-west extent from Indian perspective, and also have a lot of processing stations in the satellites itself.
No, just go on the front. It's directional.
In the satellites itself, we need to have that. So that's how the not only the processing power, the storage, and also the way we deal with these controlling satellites, that needs to be seen in a decentralized manner.
We have lots of companies, we may have heard this week, which provide ground as a segment, in fact, to help these type of satellites and constellation. Dr. Jain, any comments on this?
Yeah, Tony, you have touched the right point. Generally we tend to ignore, and the ground segment is very, very important. User terminal as well as user segment as well as the core network. And of course, the now technological advancements are coming up. The various types of antenna, additive manufacturing, and all things are coming up. But this is the biggest challenge, because with especially with the smaller CubeSats and all, it needs a large number of stations, ground segment across the world, and that is very important. But of course, now we have the inter-satellite connectivity to somehow to take care of, at least to some extent, reduce number of the requirement of the ground segment. But the focus has to be there on that, and hopefully that the cost of the ground segment would come down. That is the most important factor. Right now we are seeing in India itself, especially when we are talking about the smaller satellite, amateur satellites and all, the cost is already now in thousands. And we expect that in tens of dollars probably the cost should come. Then only it is going to be really successful, especially when we talk about the broadband, direct to consumer broadband especially, and all that.
Yeah. Thank you.
The ground, when you talk about ground segment, there are multiple aspects of it, right? One is the communication between the space stations to the ground station, space stations, anything spacecraft. And then there is antennas, ground station antennas, and then getting the data into the cloud, and then downstream data processing. So the whole thing has to really significantly improve, in my opinion, because today, even for doing a TT&C, there is no standard way of doing it. Anyone trying to actually solve that problem, it's going to be an interesting one. That's number one. Number two, we are talking about just the hardware here, building ground stations and stuff. Again, I'm going back to the best principle of making the software, make simple available for that, because just having the hardware is not going to cut it. Whatever happened in the ground segment today, the terrestrial cloud, the hybrid cloud, if you go today, if you're talking on a cell phone, go from one place to another place, you don't even know how many ground stations you hop through. That kind of technology has to come down to the ground segment. Otherwise, thousands of satellites orbiting around, you're not going to be able to communicate effectively. So that network, whatever the innovation that happened on the 5G, 4G, 6G now, the terrestrial ground, and the cloud computing, that kind of technology has to go to space. Therefore, we can have this very simple mesh network communication, make it easy for people to hop around, have a quality of service, arbitration, everything. That has to also happen in the next few years.
Dr. Murthy?
Actually, with so many satellites up there, we cannot imagine so many ground stations. Definitely, it's a very big problem. And every problem is a starting point for innovations and business. Okay. So, in this, what I teach our students and staff in the universities is, you make it in such a way that there are two kinds of communications from the satellites to the ground. One is to maintenance of the satellites. Second one is the data that comes to the ground. So maintenance of the satellites have to become more autonomous, so that ground stationless maintenance of the satellite is the future satellite, actually. That a lot of people also should ensure that. Second one is the necessary data that has to flow down as a product reduces a lot of data rates, because the product comes for 80%. Okay, you don't require big data channels for that. And only some 20% requirements of the total service requirements should require, definitely there are centers, okay, and that has to buy. Today, two things I have seen. One is, one paper came, I think girl has received this thing. In fact, I went through that paper, airships acting as a ground station. You see, the intermediate ground stations. That means you don't really require to have a fixed ground station on the ground. An airship acts as a ground station for multiple satellites in the range, and then transfers the data to the ground. So that's a very good concept. Second one is the Wi-Fi networks that are going to develop in the ground. Okay, I still have not totally understood that. So, but that appears to be reduced this thing. Otherwise, you cannot have so many ground stations, I imagine. Yeah.
Yeah, and let's not also forget that the data coming down from those satellites needs to be also processed, and that will take time and money. When actually, as you said earlier, you can process there directly at the satellite, then basically you can reduce the bandwidth requirements as well. Yeah. So because we have little time, I will take some questions from the audience now. Venkat, first one.
Yeah, that works. So again, I am very thankful and fortunate to be able to be here, and I thank the whole fraternity of SIA-INDIA for allowing me to be in this event. Now let's quickly jump to the questions. Like CubeSats are quite small, and they're pretty small. Some people are making it as small as a Rubik's Cube. So due to its small size, doesn't it pose more threat and more problems in space debris?
Who wants to take this?
If I understood your question, Venkat, you're saying there are small satellites, they're in such large sky, so how do you control them? That's what your question is?
Like if all the small satellites are going up, small CubeSats going up, are they eventually going to be space debris? So how are we going to deal with it?
Yeah, so what happens is, when you look at a satellite, you have to see from what service it offers you. Let's say it is sending you a video. If I can do it with 10 kg satellite, it will be much better than having 650 kg satellite. So when the 650 kg satellite disintegrates, it's very difficult to bring it down. But if it is a 10 kg satellite, we can deorbit it, bring it down much easier. Controlling it is much easier. Launching is much easier. So you can launch 1,000 satellites in one go than launching 36, 37, 40 satellites, right? So we have more services that are available. Yes, they can become space debris, but we have ways and means of controlling that.
If I may say something on this, there is a body at the United Nations to look at the space treaties and how you can try to avoid space debris, basically. But here, it is the industry that needs to self-regulate itself on how to actually manage the space debris, because at the United Nations, unfortunately, these discussions become very politicized and very political. Then nothing is going to happen, at least for now. So there are bodies now within the world, the ISO, for example. There is some other industry-led bodies that are actually trying to have the industry control the space debris. Venkat, because we have very little time, if you don't mind, I'll take your other questions at the end, maybe. I would like to take maybe other questions first.
Sure, we can talk later.
Yes, please, thank you. Who would like to ask a question? Just a second.
Yeah, my name is Samir. I am the founder of Avionics Technologies. So I have already worked on 2-3 cube satellite prototypes, one for amateur radio and 2 for research purpose. My question is actually for Jayaram sir or PK sir. Yesterday also a lot of discussion was going on that we are lacking in manufacturing of so many, like solar panels are there, semiconductor devices are there, or even sensors. So I do have colleagues from Israel or Ukraine, even though Ukraine situation you all know. So the quality of sensors, what they have integrated in their cube satellites, is not the same at par, I would say, what we have. And we try to acquire either from China or whatever way. But we don't have our own sensor-based industry or something. So how InSpace or, Government of India is planning to integrate and help facilitate startups and everyone?
Yeah, thank you for your question. See, as far as InSpace is concerned, of course, the InSpace is doing its bit to handhold these startups and all, especially for letting them to use the very high capital intensive test facility, which is not possible for startups to own themselves, to use them for the testing purposes and all. But when it comes to the procurement of the component level, I think that we need to develop an ecosystem for a manufacturing of the various subsystems and component level at India. And of course that industry has to come forward for that. But I think to start with, let us have the realization of the entire satellite first. and then come to the component or chips level. Till such time, we have to probably depend upon the outside market. Reliability-wise concerned, as we have been discussing this, when the cost comes down, the reliability and quality, there is a compromise. But again, the solution is there, that now the software-defined networks and all that things are coming up. Actually, that I wanted to tell about your ground segment. Probably that is one of the solutions which people are talking about, the software-defined radio network.
I'm Nikhil Arora from Space. So my question is to Karthik. Now we were talking about software-defined networks and software-defined radios till now. You are proposing a software-defined satellite. So when you are doing it, how you are ensuring the IP of the people when they are doing an algorithm, suppose I'm writing algorithm of attitude control, which is proprietary in nature for my satellite, like what I'm the attitude control I'm doing. So how it is protected in the open source software-defined satellites?
That's a great question, which I have not addressed during Keynote. So the way it's going to work is that the open source element of the software is going to give you the platform level services. Platform level services and APIs that are necessary for any third party. In fact, even you can bring your own security algorithms to connect to our software. When you talk about your payload can be a completely black box. It can be containerized or it can be in a VM scenario. So there are APIs and hooks that allows third party software to be treated as an application. So for example, you can have ADCS software for yours that can be a completely microservices kind of application that you can have. Our software will work on top of that as a wrapper API that is going to be connected to the rest of the flight software for flight operation dynamics, command and control, whatever it is. But it has no knowledge about your control algorithm because it's talking through API. So you can bring your own algorithm. You can have somebody else's algorithm come to. That's a flexibility of this whole microservices-based distributed compute architecture that we are talking about.
Okay, thank you. I think we have to now stop because we are past 15 minutes of... Go ahead, please. Very quick.
Yeah, good morning, everyone. My name is Raghava. So you all were talking about onboard data processing in space itself. But my question is, like, if there is any malfunction and the ground station is physically in the ground, a human can go and tackle that problem. But in space, that won't be possible. And I'm sure there will be a lot more complications also. So how would that be tackled?
Maybe I can answer that question. You're absolutely right. There is no human in space to really fix the problems. This is why the software and hardware that is going to space has to be self-resilient. Right? It needs to be fault-tolerant. So more and more we think about making it fault-tolerant instead of building a very monolithic way of hardware software. As I don't know if you saw the architecture I was proposing earlier. It's make it more microservices so that the component level simple failure can be detected and fixed. And also, if you have edge computing kind of things on board, what happens is you can, over the time, learn the telemetry of these components. You can predict the failures ahead of time before it happens. So these are the best practices that we are already doing in the ground terrestrial world. We're going to bring it to the space so that we can avoid some of the failures that we have seen in the past using data that we have, and also predicting those things by using algorithms in the space itself.
Okay. Thank you, sir.
The very first GSO design 80 years ago was designed that it would have people on board to actually make switches of telephony, basically. So, but unfortunately, you can't live in space without oxygen and food. Thank you to the panel, and thank you for attending the session. I just want to thank our colleagues and with all this experience in small satellites, and I wish you very well continuation.